In this topology that we've seen, each of our switch ports belong to a single VLAN, and that's great when we're connecting accounting or sales computers into the switch. They should belong to an appropriate VLAN. However, we're a little suboptimal in the way we're interconnecting our switches and the way the switch is connecting to the router. Here, notice that we've got two VLANs, so we have a couple of physical links, one for sales, one for accounting, interconnecting our switches. Same thing as the switch goes to the router. We're dedicating a physical connection per VLAN. Obviously, that's not going to scale very well. If we have multiple VLANs, then we would need to have multiple physical ports, and that suddenly spirals out of control. What we can do to overcome this limitation is to configure our links between our infrastructure devices, between our switches, between a switch and a router. We can configure those links to use not access ports, but trunk ports. Here's what that would look like. By having a trunk connection between our switches and a trunk connection between the switch and the router, now we can have, if we want, just a single physical connection, and it gets to carry traffic for all of the VLANs. That's a lot more efficient for us. An obvious question at this point is, how do the switches know what VLAN a particular frame belongs to? What we can do is color our frames. We can tag our frames as belonging to a particular VLAN. Let's say that we've got a frame coming from an accounting computer going into our switch. When the switch sends this frame over the trunk, it's going to send it with a tag. The tag is going to say that it belongs to the accounting VLAN. It's actually going to use a number, but metaphorically it's going to say it belongs to the accounting VLAN. And when the switch at the other end of the trunk gets it, it sees that, oh, this goes to the accounting VLAN, and it knows out of which port to forward that frame. Let's say that we have a frame coming from the sales VLAN wanting to go to the accounting VLAN. Here's our sales frame. It goes into our switch port. When the top switch is sending the frame down to the bottom switch, it's colored differently, it's marked differently. When the bottom switch gets it, it sees based on the tag on that frame that it belongs to the sales VLAN. It's going to send that frame down this trunk link to the router. The router is going to receive the frame in on one sub-interface, we're going to call it, and that sub-interface is just a logical division of a physical interface on our router, and we have one sub-interface per VLAN. We're using just a single interface. Maybe it's a fast Ethernet, maybe it's a gigabit Ethernet interface, but we're going to receive the sales traffic coming in on one sub-interface and send it back up another. And when the router is sending that frame out to the accounting VLAN, it's going to have it tagged as belonging to the accounting VLAN. It's going to be colored differently. It's going to go into the switch, and the switch is going to send it out an appropriate port to this accounting computer. To sum up what's happening here, we're using a single physical connection between our switches, between a switch and a router, to carry traffic for multiple broadcast domains. In this example, we're only using two VLANs, two broadcast domains, but we could carry dozens of VLANs if we needed to between these switches by coloring them differently. Now, we've been saying we're coloring them, we're tagging them. Let's talk about that with a bit more specificity. How exactly are we marking these frames as they go between our devices? What we're seeing on screen right now is the format of an IEEE 802.1q frame. This is how we're going to tag our frames as they travel between our switches. An 802.1q frame can add 4 bytes, 4 tag bytes to our regular Ethernet frame. Inside of these 4 bytes, we have 12 bits that identify the VLAN to which we belong. So we've got 12 bits identifying the VLAN. Something else that's interesting is that we have 3 bits that specify the priority value of this frame. In other words, a quality of service, a QoS marking, and we can train our Cisco Catalyst switches to pay attention to that marking and treat frames differently to give a frame a higher priority or a lower priority based on the way these bits are set in the tag bytes. This is how our switches keep those frames separate. However, there is an exception. This is a super important concept. I want you to know about something called a native VLAN. A native VLAN is not tagged. There is no tag on our native VLAN that flows over a .1Q trunk. All of the other VLANs are tagged. And when we configure our trunk, we can specify what VLAN is the native VLAN. Of course, this implies that both switches, the switches at each end of a trunk, they need to agree on who the native VLAN is. Can you imagine? One switch says the native VLAN is 100, the other switch says the native VLAN is 200. Well, I'm sending a frame that's untagged. I'm a switch and I think the native VLAN is 100. It's received by a switch that thinks the native VLAN is 200 because it's not tagged. And that other switch sends my frame out of a VLAN 200 port. That's not what we want. So we need to be super careful and make sure that our switches agree on what the native VLAN is for a specific trunk. Now that we have an overview of how we can send traffic for multiple VLANs over a single physical connection, over this special trunk connection between our switches, let's see how to set it up.